All right, welcome everyone to another OCP tap call. This is call number 125. We have Kemal Shafak. Kemal earned his Bachelor of Science in Physics from Middle East Technical University, Turkey in 2009, followed by a Master of Science in Photonics from the University of Jena, Germany in 2012, and a PhD in Physics from University of Hamburg, Germany in 2017. During his graduate studies, he worked as a research assistant at the Fraunhofer Institute for Applied Optics and Precision Engineering from 2010 to 2012, and at the Deutsche Elektronen-Synchrotron from
Synchrotron.
2012 to 2016. Since 2016, he has been with Cycle, where he is now the Chief Product Officer, leading the product development in optical timing, distribution, and synchronization systems. So today's talk will be about femtosecond precision fiber optic timing distribution and synchronization. So with no further ado, Kamal, the floor is yours.
Thank you so much, Ahmed. Sorry again for the confusion. I was waiting somewhere else, but now we can start with a few minutes delay. So thanks you also for the introduction. So let me briefly show you the outline of my talk today. So I will start with an introduction, just one slide about Cycle, and will tell you who is counting femtoseconds, where it's needed, and then I will jump into the femtosecond level timing and phase detection. So to be able to distribute femtosecond level signals, you need to be able to first detect them. There I will compare and contrast two methods. One is electronic phase detection. The other one is optical pulse timing detection. And then based on these two detection schemes, one can actually then distribute the signals with fiber optic links. And then these two methods also then correspond to continuous wave laser method and the femtosecond laser method. I will show also some measurement results, how they compare with each other in terms of interfaces and in terms of stability, phase noise. And then in the last few slides, I will show a few examples of developed systems where we installed in some facilities, and will likely show you also a few anecdotes about our future directions. So yeah, so who are we? Cycle is actually located in Hamburg, Germany. We are a spin-off from a German accelerator facility called Deutsches Elektronen-Synchrotron. And our founder is Professor Franz Kärtner, who was a tenured professor in MIT, started working on femtosecond laser development and their applications in 2008 in MIT. Then later in 2013, he moved back to Germany, to DESY, and he basically founded then in 2015 our company. So I did my also PhD with him in the similar topic, and we started 9 years ago, and today we are approximately 35 people, very international, from 13 different countries, and we are delivering turnkey optical fiber optic systems worldwide. Our major customers currently come from big scientific facilities such as accelerator centers, such as our home institute, space ground segments, and high power laser facilities. So I'm a physicist, also a laser physicist. I'm very familiar with femtoseconds. I guess many of you is also familiar. Just let's mention it one more time. Femtosecond is actually a millionth of a nanosecond, millionth of a millisecond. So millionth of a nanosecond. It's actually mind-blowingly short. To see it in a different way, in a second, light travels 7 times around the world in a second, and if in a femtosecond, it can only travel a fraction of the human hair. Here is a microscopic image of a human hair, and if you also zoom into a certain small fracture of the hair, which is only 0.3 micron long, that is how long the light goes in a femtosecond. So also briefly, let me put it into the middle. There are now light sources which can produce telecom 1550 nanometer light pulses in femtosecond regime. I do not want to describe them in my talk because they are whole topic for graduate physics studies all around the world. But let's assume they exist. I know them. So if you ask ChatGPT, can you give me a technical, artistic description of a femtosecond laser? That's what ChatGPT showed me today. And then, funny enough, it's very similar to the femtosecond lasers we are currently producing. And there are in the world hundreds, if not thousands, laser companies who actually produce similar types of lasers. So let's assume there are really, there are femtosecond lasers exist, and you can easily buy them off the shelf. So what can you do if you have such short light sources? Let's maybe, as a first example, think about a bit simpler example. So high-speed photography. So here, probably some of you also seen this image before. In 1964, some students in MIT, they were very curious about what you can do with synchronized flashes and shutters, and they were able to actually devise an apparatus, and when they synchronize the flash with a shutter within few milliseconds, they could actually take breathtaking images of, for instance, of a bullet piercing through an apple. And if you take femtosecond lasers and synchronize with each other, and let's say you scan their delay with respect to each other, here's an example that what you can do. So here you see a very complex organic structure. So something like amino acid. On the top left side, what you see is a certain charge distribution. So yellow is negative and purple is positive charge distribution. And if you scan, let's say, an optical laser with an X-ray with few femtosecond steps after synchronization, you can really see what happens, let's say, in an amino acid when it's exposed to an X-ray radiation. So you can really image ultra-fast phenomena. Yes, so who then counts femtoseconds? Why we exist? Why our business is relevant? First of all, I think this story started with particle accelerators, and with very specific one of them. So the X-ray free electron laser. So here you see, maybe let me show with the laser pointer. Here's an aerial photo of Stanford Linear Accelerator Center. This is adjacent to Stanford University, and there is one of the largest lasers in the world called LINAC coherent light source. It's the electrons injected into the facility somewhere 4 kilometers away, where they are ending up shooting towards the Stanford campus. The electrons are basically accelerated for 3 kilometers to ultra relativistic speeds, and then they exposed to very periodic magnetic structures. So if a charge sees an electromagnetic field, they emit photons. And if you do that very right, and over a very high periodicity, you can actually extract any light you want. And that's how you do a X-ray laser. So this is one of our examples, also one of our major customers, Stanford Linear Accelerator Center. There is also the European version of it. We call it European X-FAL. It's actually in our campus in Hamburg. This one is also somewhere between 3 to 4 kilometers long. And basically, these facilities need to synchronize microwave sources with optical lasers, less than 10 femtosecond, facility-wide distribution. So this is how we started. And then we realized in the last 5 to 10 years, space ground segments, especially deep space telescopes, they also progressively would like to have better frequency stability and distribution stability. So some examples, for instance, ESA's ASTRAC network, NASA's Deep Space Network. We also work now, for example, with a private satellite operator, KSAT Lunar Network. They are going to install around the world specific lunar 15-meter dishes to communicate with the moon much faster. And then there are also some more sophisticated antenna arrays, such as the one in Atacama Desert in Chile, Atacama Large Millimeter Array. So their main spec they are trying to fulfill is about less than 1 picosecond RF over fiber drift over hundreds of meters. And in terms of phase noise, they are trying to achieve minus 100 dBc per hertz at 1 hertz offset frequency for 100 megahertz carriers. So it's also quite challenging. It's basically, again, counting femtoseconds. And what we see currently developing, there is a need for compact photonic signal generators, especially if you are moving from 10 gigahertz to higher frequencies, effectively achieving very low phase noise. Oscillators about 30 gigahertz is quite challenging, and photonics and optics is give quite promising, let's say, at least experimental results. So this could be used, for instance, for autonomous driving. So, and what they are looking for is something like an optical oscillator with minus 130 dBc per hertz at 1 megahertz offset from a 77 gigahertz carrier. Or they are also generally trying to develop on-chip oscillators, optical oscillators with the basically capability of generating ultra-short pulses. So basically, they are trying to squeeze these shoebox lasers into chips. And some other applications, by the way, all these applications, 3 of them I mentioned, we are more or less active with it: particle accelerators and phase ground segments. We have operational systems, and currently we are working on R&D with several industrial partners on the compact devices. But there are also other possible applications for femtosecond optical timing distribution, high bandwidth, some of them high bandwidth, low latency telecommunication. High power laser fusion is upcoming. There's a lot of money flowing nowadays to laser companies, especially if they can actually make laser fusion. Maybe you have heard X-light, FEL-based lithography sources. So lithography needs UV pulses. If not, maybe if you have an X-ray, it will be better. So now there are some companies working on ferroelectron laser-based lithography sources. There is one called X-light in America. And obviously something we are all excited about, the quantum networks, and these guys probably will need to take a look at this kind of systems. Okay, so this is the introduction. Let's take a look how you can detect femtoseconds. And let's start with femtosecond laser. So if you have a femtosecond laser, you have an ultra short pulse train, and its repetition rate is around 200 megahertz. And you would like to detect its timing, its center of gravity in time. The simplest thing you can do, you can put it on a photodiode. The problem is that we don't have electronics which are fast enough to resolve femtosecond optical pulse train. So what the photodiode does, even the fastest one, it creates an electronic pulse train whose shape is a bit distorted with respect to the femtosecond optical pulse. Obviously, it's much broader, so you are getting basically picosecond, hundreds of picosecond durations, and its shape is also very dependent on not the femtosecond lasers, but to the photodiode. But there is a trick we can do. So let's see, you are from the oscilloscope, you connect to the signal analyzer, and what you're going to see in the spectrum electronic spectrum analyzer is a COM. So you will see distinct frequencies at the repetition rate of the femtosecond laser. And if you filter one of them with a simple electronic bandpass filter, what you see is a pure, nice sinusoidal signal, with whom everybody is familiar and comfortable with. And the good thing about it is that, okay, then you can have the reference source or a reference laser. And the good thing is about that the phase of the photodetected signal is directly related to the center of gravity of the optical pulse. And when you do a mixer and low pass filtering, so between these two oscillators, you will have a sinusoidal function whose frequency is equal to the difference frequency of the oscillator. And its zero crossing response will be the phase sensitivity. So what you get usually in terms of sensitivity is something like 1 microvolt per femtosecond. So if you want to detect femtoseconds, 1 microvolt response is a bit low. And the worst thing is actually also it has a lot of very different noise sources from the photo detection, space charge effects in the semiconductor device. It's also thermally very sensitive. So if you need to stabilize basically the PCB, let's say with millikelvin stability, even then it's very difficult that you can get few femtosecond stability. But the good thing about this is very cheap. You can have a simple integrated circuit, and you can make it very compact and very cost efficient. But you are really dedicated, you would like to measure femtoseconds, you would like to do it right, and then you can do maybe an optical domain. So let's say you have 2 femtosecond lasers, you optically combine them on a single beam, and you run it to an optical mixer, which I will call a nonlinear crystal, is basically an optical mixer. So you run them, focus them into the crystal, and depending, these are femtosecond pulses, by the way, depending on their temporal overlap, they will create some frequency, and then you are going to filter this. Yeah, so here I show basically the certain overlap between these two pulse trains. And depending on this overlap, the energy in the some frequency pulse is different, right? So this is a good thing about it. So now you don't have to detect the pulse duration. Yeah, you have to only integrate the energy of the some frequency pulse. So you'll just count, let's say, charges. It's very simple. You don't need a fast photodiode. And let's say you can scan these two pulses with respect to each other with delta t with a simple delay line. And then you will get a very nice cross correlation curve on the photodiode output on an oscilloscope, which is also, quite easy to work with. The problem is, life is always not so easy. The intensity noise, let's say the green pulse has intensity noise, obviously that also changes the energy of the pulses. So this is basically giving you amplitude modulation on your optical cross correlation curve. So now you don't have, if you have intensity noise, you will not have for one, let's say, certain time difference between the two pulses, you can have different readouts. Yeah, so you want to get rid of this, but it's the way of doing it is also quite easy. Let's say you do another cross correlation with the same pulse trains, but this time they are time delayed with each other. So the cross correlations are time delayed. Maybe this is a simpler way to picture that. So you have the same cross correlation curve. It's also amplitude modulated, but they have a time delay between each other. So then you have two photodiodes, and let's say you subtract them from each other, and you get something very nice called S curve. And here, especially around this middle zero crossing, the intensity noise of the lasers are suppressed, and you have a very nice, attosecond level resolution, phase, and timing sensitivity. Good thing is about that this is pure crystal. Yeah, it's like really thermally stable. There is no charge effects. It's really durable against thermal effects, charge effects. So it's also not sensitive to the environment. The only problem is that it's a nonlinear process. So you need femtosecond pulses for sure. Picosecond pulses will not work. So that's why you need to work with femtosecond lasers. Let me show you actually when we first built such detectors, they were, half an optical table, but right now you can have integrated photonic circuits. So we have a integrated detector with an American startup from Montana, EDVR. So it will be, it's actually like packaged, fiber packaged detector. So it could be also quite small nowadays. So the technology is advancing. So let's take a look how they compare with each other. I had in the lab two femtosecond lasers. I had set up an optical cross correlator and an electronic detector, and then I put their outputs simultaneously to an oscilloscope. And that is the video I'm going to show you. The yellow curve here is the microwave phase detector output, the sinusoidal signal. The frequency difference between the two lasers are 400 hertz right now, and around the zero crossing, you see the phase sensitivity of the electronic detector. And take a look at the blue curves here. They are only spikes right now, but I'm going to zoom 3 times in time with the oscilloscope. And only then you see the sensitivity of the optical detector. And here, the yellow curve is just flat, right? So you can see the optical detector itself is much steeper in terms of phase sensitivity. And here you see the also individual cross correlation curves. Okay, so then you can build a feedback loop. Obviously, you can synchronize them with each other. So let's say you build your electronics and you are tuning the oscillators closer to each other. Obviously, they are going to get an almost zero frequency difference, and the PID activates itself when it sees the threshold signal. And you see, after even locking, you see fluctuations existing on the optical detector output. So this is a way actually also to characterize remaining noise from this signal generator. So that also shows you the detector still detects the residual signal, which is on the duration, on the magnitude of, let's say, attoseconds or few femtoseconds. Okay, so we talked about detection. Let's take a look at the systems to transfer them to remote locations. So if you have, let's say you want to build a system, you are happy with electronic microwave phase detection, then what you can do, you can build an RF over fiber system. And your goal is, let's say like European Space Agency has, you want to transfer maser type of stability, then you better build an RF over fiber system which is actively stabilized. So what we do here, we have an RF input let's say 100 megahertz, and we inscribe this 100 megahertz wave on a continuous wave laser with using an electro-optical modulator, and then we go towards the transmitter and to the receiver, and a portion of it is reflected back, and it comes with a circulator, and it's compared with its reference signal using the electronic phase detector. Then you activate feedback on an optical delay line, or you can also activate on an electronic delay line. And then on the receiver side, you filter out whatever you would like to do. So this is a system RF in, RF output. So good thing is about that, if you do unstabilized, you can have just cards, transmit, receive. But if you want to do something stabilized, maybe you will have 1U, 2U, 3U systems. And yeah, so they are highly compatible with microwave equipment, and their front end is very simple. They are relatively cost effective. The problem is that if you want to go, let's say, from 100 megahertz to gigahertz, it will require up and down conversion, and it's relatively noisy. And you want to do it, let's say, with the femtosecond lasers. So in this case, your transmitter part will look a bit different. So what you will have, instead of a CW laser, you will have a femtosecond pulse laser, and you will lock this pulse laser to your RF input. Yeah, so you will need another PLL here, optical PLL. And since femtosecond lasers, you would like to use one femtosecond laser, is expensive, so 40,000-50,000 euro, $. You would like to use it for multiple links, so you will build a splitter, and then you will have for each splitter output a transmitter module. Yeah, it's basically an optical delay line with an optical detector. So then basically in terms of footprint, it will be at least 6 site units, which is the size of the ESA system we have. And then you go to the remote location. So if your customer would like to have RF output, you can photo detect and filter it. Of course, you can again do back reflection, and you do timing detection and compensation in optical domain. But you can also simply deliver optical output. Nowadays, maybe you guys are familiar with optical clocks. So they in the future there will be hopefully clocks similar to masers, but they are running on optical domain, so you can directly give an optical output. Yeah, and the receiver footprint is about 3U. So advantages is highly sensitive, as I showed you previously. It's actually more compatible with future optical clocks and frequency comms. It's excellent in terms of long-term and short-term performance, which I'm going to show you next. But it's relatively complicated. Of course, optics are not as mature as electronics. They are more expensive. And since you do femtosecond pulse transmission, it will require dispersion compensation. So yes, so let's take a look at the performance between CW method and the femtosecond laser method. By the way, was there a question? If you want, I can pause for a while. But
I think
otherwise,
it was just noise. I
okay.
muted.
Good. Then let's take a look at the performance comparison. We call it wave versus pulse. Yeah. So here we had a wave transmitter. Let's say it was at 2.856 gigahertz, a common frequency for accelerator centers, and we pulled back the RF receiver and we did additive phase measurements, and we did the same thing for the pulse system. So, but this time we did both in the RF domain. So what is the stability if you extract an radio frequency there? Good thing about pulse system is that when you photo detect, you will have all the harmonics. So if you have, let's say, 238 megahertz laser, you can have all its available harmonics. So you can go, if you want, directly to 40 gigahertz. But in this case, we went to 5.7 gigahertz. And we also measured, let's say, optically added timing jitter. So, and then let's compare this. So here is a phase drift measurement for the stabilized RF over fiber system. If you do it right, if you do it good, you can actually really get better than 100 femtosecond long-term stability. So here you have 2 hertz sampled out of loop phase measurement, and the RMS drift over 8 hours around 40 femtosecond. And then if you do this for the optical to optical signal using pulse system, what you see here is a substantially lower drift. Yeah, so here we have 60 hours of measurement, and the timing drift between the input and output optical signal is 1 femtosecond RMS. And here the scale is from 100 to minus 100 femtosecond. And in this case, we had from 400 to minus 400 femtosecond. It's really more than a magnitude, order of magnitude better stability if you do optic in, optic out. Now let me show you, maybe some of you are more familiar with Allen deviation, fractional frequency instability. This is an additive measurement again. So here you can find the data points. So the black curve is state-of-the-art hydrogen masers. Yeah, so they start at 1 second integration averaging time, something like 6 10 to the minus 14 fractional instability. The gray curve is the wave RF over fiber system. It's has instability better than, lower than masers. And then the blue and yellow curves are the pulse system. So the blue one, if you extract from the pulse distribution and RF signal, it's still better than the wave signal, but it's more or less, similar order of magnitude. And if you do it optically, obviously, your detector is also more stable, so you can have easily more than an order of magnitude higher stability. Yeah, but of course, if you do an optical system, so you can only interface with optical sources. All right, so this is the comparison. Let's take a look at the, let's say, some of the examples that systems that we developed. For instance, here I'm going to show you European Space Agency's second generation optical FNT system. So what we did is basically we interfaced this RF over fiber or pulse system, optical systems with conventional electronic frequency and time hardware. So they have two masers in a deep space antenna. And what we do, we take 100 megahertz from these masers. We generate with FPGA local time, 1 PPS. We also generate IRIC code because they need for some old antenna subsystems. And then we also take the 100 megahertz, divide it down electronically, 10 megahertz, 5 megahertz. These are all simple electronic division. And then we take the 100 megahertz and use this for transmitting to a remote location where they may have, let's say, deep space dish to transfer with femtosecond level stability to the remote location. So as you see, the optical FNT transfer can be really nicely interfaced with state-of-the-art conventional electronics. So here's an example. We call it master time generator. For instance, this unit has GNSS receiver, 1 PPS, local time generation. And we also have a phase frequency meter where we would like to see the frequency drift of the locally generated frequency with respect to the masers. Obviously, we have tick channels where we measure the local 1 PPS with respect to the GNSS so that the station knows what is this GNSS drift and can compensate for it every week when it's more than 100 nanosecond. And if you do it a system like this with the front ends, you will have a rack system similar to this one here. So we are coming almost to the end of my talk. So I will just briefly show you our flagship projects. As I told you, we started with accelerator facilities. We were able to cover 3 continents, including Japan, China, Italy, and the States. Then our customers come from high power laser facilities. There is one in Arizona. Arizona has a compact free electron laser where they want to use laser plasma acceleration for X-ray generation. Yeah, so then more lately, since starting from 2022, 2023, we actually had a really good start with space ground segments. ESA was our first customer. We already deployed 2 systems for them. And recently we got into collaboration with KSAT, a Norwegian company, and they are building the lunar network, and we are going to install 3 systems in Australia, Spain, and the States in the next 2 years. This was today. So we also would like to be a bit more agile towards the future. Future is always mass production, and also integration and making everything compactor. That's why the first project, R&D project that I would like to highlight here is called LIRAS. LIRAS stands for LiDAR Radar Combined System for Automated Driving. Here we partner with very large industrial partners such as Volkswagen Group, maybe semiconductor manufacturing company called Global Foundries, and there are also some local high technology institutes such as Fraunhofer Institute for High Frequency Physics and Radar Technique. Conrad, Saveo, there are a few other partners which are helping us with photonic integration. So what is our task? Our task is a frequency to have a frequency modulated 77 gigahertz optical signal generator based on two tunable CW micro resonator lasers. So here is one of my colleagues from my professor's group. They were able to achieve one type of laser like that. So our goal is now to precisely manufacture two separate laser diodes with exactly 77 gigahertz difference, and they will be basically frequency tunes with each other. When you interfere them, you will have a 77 gigahertz optical signal generator. The next one is more, I would say, less industrial, but more ambitious and more oriented for research. We are basically trying to devise a femtosecond laser-based integrated frequency comm, which can be used also for photonic microwave generation. So the challenge here is to really manufacture on chip CMOS compatible femtosecond laser. And this is highly nonlinear phenomena. There are very complicated physics involved. That's why you see the partners here are mostly research partners. Ligentech is, for instance, a photonic integrated circuit fabricator in Switzerland, and we are also partnered with some Dutch and some German partners. I think that's all. So thank you very much for your attention. If you have any questions, please, I'm here for it.
Great. So let's open the floor for questions. Maybe I can start like an icebreaker. So how far are we in femtosecond? Because like the moment you go sub-picosecond, you call it femtosecond. Is that the case?
So right now you can buy off-the-shelf lasers whose pulse durations are 20 femtosecond. And
20,
yeah,
okay.
the cost will be something like, 20,000, starting from 20,000 euro. And the ones that we are trying to produce basically pulse durations shorter than 100 femtosecond. And yeah, we have some promising results, so to say. But it's challenging to make it on chip. Yeah, so I'm not an expert on that, but that's why it's going to take some time. Yeah.
In terms of synchronization, which I mean, it's like the main, I'll say, interest of this this group.
Yeah. So
yeah.
So your question is how tight you can synchronize them with each other, for instance, or?
Yeah.
That's why I actually wanted to show this graph here. So this is more or less what it shows you. So we basically had, as I told you here, I'm sorry, a pulse laser. We put it in a link and then we fold it back here. Okay, we compare something like fiber traveled pulse with each other. Here we can actually see they are very well synchronized with each other. So 1 femtosecond. But if you do that with two independent lasers, which we also do, then you can actually get maybe on the order of 10 femtosecond. Actually, I have a slide, I guess. Yes, it's this one. For instance, here we synchronized on this. Our detector is, by the way, called balanced optical cross correlator. So we have a master femtosecond laser and a slave femtosecond laser. So here, if you build a PLL with this one, so on timing jitter from 1 hertz to 1 megahertz, something 6 femtosecond, and long term is something like 10 femtosecond. Obviously, it's a bit more challenging than just simply stabilizing the fiber, but you are again on the orders of tens of femtosecond at most.
And when you put it in like comparison, let's say with White Rabbit, how would it stand? It's pretty much the same. It's like DMDT, isn't it?
So I am not a White Rabbit expert. White Rabbit, I think, is sending digital coded signals over fiber, and then they are basically reading out, and the PLL is also digital. And I haven't actually seen a system where White Rabbit can do few picosecond stability. Yeah. So, and what they use there, they don't use femtosecond lasers. They use simple small form factor, laser diodes, and their pulse durations are usually nanoseconds. So at least I was in contact with some Safran colleagues. So they have, a department there, and they are telling me, especially for data center synchronization, some customers are asking for them. They cannot breach, comfortably tens of picosecond stability. And it's also, if it's long, they have a dispersion effect as well. And if they don't manage dispersion well, they are not optical scientists, so the data packages will overlap with each other. So they are usually doing a repeater station or something like this. I think for them to come to breach, let's say, 100 femtosecond barrier is very challenging.
Ahmed,
sorry, go ahead.
I'm also interested in this, and I'm sorry if I'm interrupting. So I do see differences versus White Rabbit, and maybe Kemal, could you go? I'm not sure I understood. I'm also joined a bit late, so maybe I lost. But is your correlation two-way? Are you sending back and forth over the same fiber, or is it just one-way synchronization? How?
Yeah, so at least our wavelength is one fiber, and we have an optical partial reflector. We basically do two-way transmission.
Okay,
if that's the question. Yeah. So we don't do two-way. We basically have really dedicated transmitter and dedicated receiver. We don't do transceiver, so sending two ways and local. This can be also implemented, but that's why we did it with a two-way. It's a bit traditional that we actually first started with femtoseconds. Having 2 femtoseconds on each side is more expensive, so we are very familiar with back reflection and two-way compensation. But I think you can also have a two-way transceiver system.
The question is related, maybe in my view too. So you are showing very high level of resolution and what I would call in my terms ability to synchronize, to provide frequency, but if you're not doing, or maybe I'm missing something, any two-way measurements, then you can have phase drift due to changes in the delay over the fiber or any other aspects related to that.
Yeah, so that is a limitation, because if you do two-way transmission, the fastest feedback loop that you can basically have is should be so the length of the fiber limiting factor. Yeah, so but if you have, let's say, 5-kilometer fiber, the round trip time or frequency will be 100 kilohertz. Yeah, and 100 kilohertz. So when you measure the noise of a fiber, you usually have mechanics, nothing. I don't see something faster than 50 kilohertz disturbance. It becomes really limiting if you go beyond 50 kilometer or something, because then you are coming to a regime where it's 10 kilohertz and it's interfering with acoustics. If you are talking hundreds of kilometers, it's again, becomes your
consideration I was raising, which is something White Rabbit do attempt to address, is the fact that due to, let's say, temperature variations for the deployed fiber, you might have the delay vary over time in a manner that will cause you phase differences due to the delay of the optical signal in the fiber. That's what White Rabbit excels in addressing. So it enables you probably get much better synchronization due to your techniques, but the phase certainty of what you convey might be lower than White Rabbit, and it might not be a limiting factor for your applications if what you just need is very high level of synchronization, again, using this term.
So I think synchronization, I'm not so familiar, but let me tell you this way, why we reflect back is actually we are detecting actively what is the thermal drift of the fiber. So thermal expansion coefficient of a fiber for something like 40 femtosecond per meter per Kelvin, or 40 picosecond.
Okay, so you do have some, the reflection enables you to measure the delay variations in the fiber.
And much better than White Rabbit, because White Rabbit is sending data packs, it's digital, right? So they have to read out and say, okay, then they do the readout, in my opinion, digitally. I'm not familiar so much, but then they build a digital feedback. What we do is, if you say the RF over fiber system, we do it in an analog way. So we have really sinusoidal signals, and we do mixing. Basically, we mix with the fiber traveled 100 megahertz signal with a fresh one, and then what you see there is obviously the thermal or environmental drift of the fiber.
Okay.
If you don't do that, you cannot.
Again, using my terms, you have both a very high level of synchronization and phase synchronization, but but you still probably have some calibrations, I don't know, that are not addressed. So the absolute phase is something that needs to be calibrated into the system, which is another thing White Rabbit attempts to address, and probably in your applications might not be a factor, because maybe the phase is constant phase might not be an issue for the detectors or something like that, or you might be actually detecting the the particles themselves or things like that in various manners.
So you're right. I think what you are saying with phase is for instance, let's say you have a second, right? So you want to know exactly when your second starts. So you don't want to have a random delay, in 1 second signal. That is correct. So because we send, if you think about it, let's say 100 megahertz or 3 gigahertz signal, it's a continuous, sinusoidal signal. So we do not, if we let's say we work at 1 gigahertz and we can actually have a RF phase shifter, we can tell the customer, okay, here is your RF receiver phase shifter, so you can tune whatever phase you want, right? But you cannot do that with, let's say, if you want a 1 second here and another second with femtosecond synchronized 10 kilometers away, you have to be a bit different. So what we do actually for ESA is a bit different. So if you want 1 second, so what we do, we send 100 megahertz signal RF over fiber, and we stabilize the RF, so RF thermal drift with analog microwave phase detection. And then on the remote side, we divide 100 megahertz down to 1 pulse per second, right? When you do that, the added jitter from FPGA is something like 7 picosecond or maybe 3 picosecond RMS. It's quite stable and simple and also predictive. The only problem is that your second on the master location, on the remote location, may have different, so they don't tick together. Then what we do, we also send another signal just to initially align the 1 PPA signal. So we can actually do two-way transfer. We can know the fiber delay, and we say, okay, whenever the system is restarted, derive your local 1 second from the 100 megahertz, which is actively stabilized to femtosecond regime, and then align with respect to the GNSS or with respect to the master location using your trigger signal. And in this way, you can actually align them with, let's say, tens of picosecond accuracy, and then they will drift with respect to each other with the drift that I'm basically showing here.
I'm not
That's
sure.
what,
Could you repeat how you send the signal? Because you said you have a frequency. Do you have like a pulse per second that's more accurate? Or
so what we do is also we send pulse per second. So basically simple pulse per second RF over fiber. We send it also to the remote location on parallel to the sinusoidal signal. And that is so basically that is an alignment signal. And that one, it's delayed very well because we can do two-way transfer. And there's a simple algorithm. You can know if your fiber routing is not so doesn't have differential lengths on forward and backward. So you can really align, let's say, with nanosecond with respect to your master location. So then afterwards, your FPGA runs on your 100 megahertz signal that you transfer from the master location.
so the pulse per second is again an analog fiber signal, yes?
Yes. So you can really just have a DDS directly modulated diode signal, and this is really just for initial alignment, right? So this is to show, okay, this is the tick, and then you can, obviously there is a limitation of this too, because 1 pulse per second rise time is the best ones are like 1 nanosecond or half a nanosecond. So nanosecond I think alignment is kind of a limitation due to the let's say the rise time of the 1 pulse per second signal. But otherwise, after this uncertainty of 1 nanosecond, it really drifts on the femtosecond fiber transmission drift, because it runs on the 100 megahertz
Maybe just
coming
the
there.
feedback from what I'm acquainted with high accuracy White Rabbit, and most of their efforts are that they are able on a single link to get below 1 nanosecond of accuracy due to the electrical calibrations they do. So like they get like 0.1 or something like that nanosecond or lower per link, because they are handling all of these electronic parts which you probably care less about.
Or don't know. Yeah, that's true. I think we know probably fiber optics better and the way of calibrating, let's say, fiber thermal drift, but they definitely know better electronics. So that is true. We don't really do much then simple transmit and receive for initial alignment. We do not do, cross correlation or this kind of digital analysis. Can be done. Yeah, then you can actually combine these two techniques. Maybe you can have hundreds of picosecond alignment precision on two locations, and then they will drift only, let's say, less than a picosecond for sure with respect to each other.
That's actually an option since at least in the PTP standard, the synchronization part is done in a manner that's a bit detached from the synchronization. So you could use your techniques for synchronization and get the very high rate of stability, and then do the synchronization via the already developed high accuracy PTP white rabbit techniques. So
I believe so, yes.
Thank you.
Thank you.
Very interesting.
Thank you so much.
Wonderful. Any more questions?
Yeah, can I jump in?
Go ahead, Roger.
Yeah, hi. This is Roger Rusak. I'm actually at University of Minnesota. Could you go back to your slide, well, slide 16 first? It's a beautiful plot. That's an amazing plot, the bottom one, and the top one looks very good. I just wanted to say, what exactly are we plotting here? So this is what are you plotting in terms of the timing drift? How do you define that?
Yeah, so in terms of the RF over fiber system, there we have a digital phase frequency detector, something like Hittite, HMC, some chip. So what you are comparing 2.8 gigahertz RF signal in the master location with basically receiver output at the same frequency. This is simple phase measurement, and then you can calibrate, from phase to time by using your carrier frequency. So this is quite straightforward.
You're measuring the phases of with respect to some master, which is on the receiving end, I take it. Okay.
Exactly.
Did you ever do the same thing where you took two clocks distributed in this way and compared their frequencies rather than using like a reference on the receiving end? You take two separate clocks going to two different fibers and then compare them side by side.
So let's say if you have two masers and you we did that.
Or rather, you just have one maser which you found out.
Yes, I have. You would like to see, I guess, a result? 1 second.
Yeah, I mean, so that's really the apples to apples. That's the major one. You want to make sure that what arrives in this position and this antenna is the same as in that antenna, which may be 50 miles away.
So we did that for ESA because ESA has two masers, as I showed in this plot here. We have a conference publication. Let me pull that up very quickly. So what we see, if you beat two masers with respect to each other, and then when you beat them each other in a remote location. So 1 second. This was in International Frequency Control Symposium in Japan, 2023.
Can you post the link? Actually, there's a lot of information in your talk, which is hard to digest.
Thank you so much. That makes me do. So yeah, exactly. So that's what you see here. ADA measured maser versus maser in the master rack.
Sorry, I'm seeing
you have not
your E-track second generation FNT slide.
1 second, I have to find out how we can do that.
I think somebody has to stop sharing.
New share. Okay. Let's do screen.
I'm still not seeing it. That's different. Okay.
Okay.
Yes.
So this is basically alien deviation measured by phase frequency meters. The blue curve, maser versus maser in master rack, and the red curve, maser versus maser in a remote rack. Basically identical. And so here, if you, let's say, have one maser but fan out, and then you measure in two remote location, here this is what you see, this black curve, and this is also limited by the resolution or the noise floor of the phase frequency because these are also have higher noise floor than optical signals. So if you do it in an optical way, let's say you measure two pulse trains with respect to each other, you really see a much lower floor.
Okay.
That's why I say here, this is the optical FNT system limit. If you do 100 megahertz in and 100 megahertz out.
Yeah. Okay. And then your optical signal, what frequency are you working on? What wavelength are you working at?
1550 nanometers, so telecom, standard telecom.
Standard, okay. That's a solid state edge emitting laser, or are you using?
Yeah, they are erbium doped. You have two options. You can have a solid state laser, so on an erbium doped crystal.
Yes.
There are a few companies providing. There are also fiber lasers. They have
Mode lock.
advantages, disadvantages. Mode locked, exactly. They are mode locked lasers. So you have to lock basically multi-longitudinal modes. It's a topic we can discuss more in depth. But yeah,
Okay.
so you need something like a Sutterable observer effect. You have to lock all these longitudinal modes so that they always interfere with each other with the same phase, so that you generate femtosecond pulse train. So this is
Right.
also, yeah.
Okay. You need them to be coherent to interfere. So you need to have the two sources be coherent.
To generate femtosecond pulses.
Yes.
So
No, sorry. When you do your comparison of the phase comparison.
okay, that is also good point. So what we do is optical intensity cross correlation. That's what I was trying to explain it here. So this is not interference. It's rather some frequency generation. So if you do some frequency generation on a nonlinear crystal, because this is basically optical multiplication, and the optical wave under the pulse envelope cancels each other. So what you see here, this detection method is really just sensitive to the pulse envelope. So that's why they don't need to be necessarily at the same frequency. That's why you can also mix, Roger, let's say titanium sapphire lasers at 800 nanometer with 1.5 micron lasers, because for instance, laser plasma experiments, high power lasers, they cannot sufficiently do that at 1550 nanometer for a variety of reasons. They do it rather at 1 micron or 800 nanometer. And that's what we do. Then we choose another crystal which satisfy the phase matching angles between these two wavelengths.
Yeah.
Yeah. So this is not really sensitive to the phase of the optical wave. It's rather the envelope.
Okay. All right. Very interesting.
Thank you.
Kemal, very nice talk. I had a quick question. So on slide number 16, you are synchronizing two nodes, right? What is the distance that you kept the two nodes at? Because like amazing plot, like slide number 16, right?
Thank you so much. In this specific case, it was 250 meters, the system that we install for SLAC in Palo Alto. But I have done also also in the company fiber lengths up to 5 kilometers. Obviously, the residual drift is a bit higher, but we can, comfortably be within 10 femtoseconds. So if you have a bit longer fiber, obviously it will be a bit worse, but it doesn't get to a level that is, more than a femtosecond 10 femtosecond RMS.
Okay, so you did not do any kind of temperature, control, right? It is all compensated, like
yes.
So the phase.
Yeah, the fiber is deployed. In this specific case, we actually tested on an optical lab. We have also done some measurements where we actively modulate the fiber temperature and see, what is remaining. In this case, it was really simply sitting on, a room where the AC was, something like in a day plus minus 3 degrees, so 6 degrees. So it's like slow room temperature. Yeah. And usually in accelerator facilities, you see similar environment. They are like galleries closed, and you can get like plus minus 2-3 degree centigrade stability.
Okay,
if you expose it to open environment, is a different story. Then we have to see what is the exposure. For instance, in some parts in SLAC, the optical system delay is limited by 3 nanosecond compensation, and they have a section where it's open, and they see in 30 minutes something like 20 degree fluctuation. There you need to have a faster actuator. So this is very specific, system specific. There you have to be more careful. Yeah.
Okay. Thanks.
Thank you.
All right. Any more questions?
Hey, I have a question, Ahmad. Hey, this is Nino. Great presentation, Kemal. That's correct. Is correct presentation?
Yes.
Yeah. What's the price point of your transmitter?
For RF over fiber systems, is on the order of tens of thousands of euros. It's rather on the lower end than the higher end. And for the pulse transmitters, is close to transmitter and receiver pair, close to hundreds. Yeah, it's 100,000, so 90K, 100K, depending on the fiber length, because we also have to do, let's say, dispersion compensation. Yeah, so this is also a specific thing, and the fibers must be polarization maintaining ideally, because nonlinear crystals, the polarization of the light is sensitive. So what I would say in terms of high price for the pulse system, it's due to a factor because it's not really it's not really a standard. It's really custom system. You know, there are only 1 or 2 companies in the world can do that. If actually there are more, let's say, usages for this, the price will go down. Yeah, so it's really here we are producing, let's say, 5 or 10 systems in a year, so it becomes obviously not so cost effective. That's why I was mentioning the, you know, in the comparison.
Okay, thank you.
Thank you.
Wonderful. Any more questions?
I have one question, Ahmed.
Go ahead, Ashok.
Quick one. Kemal, what are the applications for this femtosecond?
Yes, that's what I was trying to summarize in the first slide. So
yeah, I missed it.
Yeah, sorry, no problem. I was also a bit late. So particle accelerators are, you know, our first customers, specifically X-ray free electron lasers. And then the next segment were space telescope operators such as ESA, Deep Space Network, NASA Deep Space Network. There are also, you know, private operators such as KSAT, Lunar Network. And yeah, so these guys really can afford to buy, you know, a pulse timing distribution system and also a stabilized RF over fiber. So what we are trying to do is basically in the future, make them compactor, you know, cheaper. Obviously, it's also ongoing. So we have some partners from automotive industry such as Volkswagen, and we are also trying to do cheap femtosecond lasers, which is a bit more, you know, down the road. So yeah, then this will be probably then more applicable for, let's say, that's why I want to say big science to big data, right? So right now, most of the customers are big science, but if, for instance, in radar LiDAR system, they have to do very fast computation, so everything is fast, and they also want to have a very stable optical sources and transmission for that. So then we are going towards big data. I hear maybe some telecommunication companies are interested in femtosecond lasers deploying, because what they can do in a femtosecond laser, you have literally hundreds of thousands of CW lasers packed each other with very stable frequency difference. Imagine you have an optical spectrum centered at 1550 nanometer, and comm lines, you have 100,000 comm lines which are separated by 1 gigahertz from each other. So you can use for each comm line a channel. So then in this way you can actually do per channel, you can dedicate, I don't know, this nanometer for, you know, high data center volume, the other one for I don't know, for household, the other one for military. Yeah, there are some future applications maybe upcoming. So yeah, it will only show in the future. We are in the beginning of talks with this kind of customers. Yeah. Yes.
Great. Any more questions?
This is a bit off the direct topic, but I was very curious about the solid state lasers and the solid state systems you were referring to in the last few slides. How far are we along in making these type of devices? Are these still very much on the bench, or is this something we're in prototype mode at the moment?
So you mean femtosecond lasers, or?
Yeah, the femtosecond. So I think there was 2 parts. There was the femtosecond laser. Then there was, if I remember correctly, I don't have your slides in front of me, but you were talking about where you start to make the whole process within a semiconductor.
Yeah. So actually, tabletop femtosecond lasers are very common. So there are hundreds of companies in the world. That's why I was showing you ChatGPT artistic impression and our femtosecond laser. So it's basically a shoebox size, fiber in, fiber out. Yeah, it's their prices are dropping, the competition are increasing. Yeah, and then we also now trying to really go more compact on chip pulse laser systems. So for them, there are few ways of doing it, Roger, and I think the best ones maybe at least 5 years away to be really commercialized. Yeah, I'm a bit more realistic person than optimistic. Yeah, so we'll see.
But is the technology similar to a mode lock laser where you have a nonlinear region?
That's what we are trying to do. So that's why there's a small graph here. I don't know whether you still see my slide. So this is really like a waveguide based
yeah, this is
chip
what I
laser.
want. That's the slide. Yeah, it got my attention. That one. So this is, you have a WDM.
Exactly. So WDM is basically you need a pump signal to pump your high gain material. You have to have a very nice waveguide, and then on top of it, you have to deposit a gain layer based on what is this aluminum octalium. So you can read it here. It's really material science, yeah, and also it's also quite microscopic. So the homogeneity of the layer deposition. I think we are very good in silicon nitride technology. They can do it very homogeneous waveguides, so passive waveguides to direct the light. That's no problem. But making very homogeneous gain material, it's very difficult.
Oh, I see. That's the gain material which you have in your waveguide. Oh, okay. I see.
Yes. Yeah, and then you have to be able to generate femtosecond pulses. You have to have something like a saturable absorber, because saturable absorber, what it does, you always have parasitic CW radiation in your laser because it's easier for the laser to damp its energy. But if you do not have a saturable absorber, so saturable absorber basically blocks for up to certain intensity, it's opaque, so the CW doesn't work. It has high loss, but when it exceeds its threshold, where it's starting to form a pulse, and then it's completely transparent. Yeah, so that is also something like interesting semiconductor material design. Yeah, so that is also challenging. So these two saturable absorbing effect and also gain effects are not that easy to manage, and that's what my colleagues are trying to do now.
Understood. What's in this picture? What's the H1 and the H2?
H1 and H2.
So you have the racetrack, and then after the racetrack you have this.
Now that's a good question. I have to ask my colleague.
Okay.
Yes, I think they have to do some. Yeah, it will be speculation. I do not know exactly. Sorry.
Okay.
But
okay. But thank you very much.
Thank you.
Right. I have a question before. Let's see if anyone else has something. All right. So I have a question. How hard is it, or how possible is it to basically do like the synchronization or synchronization, basically from 1 to 2, extrapolate from that one from basically 1 to n.
1 to n, you mean very high numbers of remote
Clients.
locations?
No, client, like basically
client.
Yeah.
So like exactly, if you do active stabilization, you always, in our scheme, if you do back reflection, you will have for each transmitter one receiver, right? Because that's how you are going to detect the fiber. That's why it will not scale. So it will linearly, the cost will linearly scale. If you make it more, obviously it will cost less. But yeah, so you can try to, how can I you can use some symmetry someplace. Let's say you have a node, you very sensitive, 1 kilometer, you want to do 100 femtosecond top, and afterwards you can do combination of passive transmit and receive, right? There you can actually, let's say, scale your system also with much less cost. But if you do active stabilization, I think I haven't studied whether you can use some more clever architecture to be able to make it cheaper for, let's say, a very high number of distinct nodes and distinct locations from a certain master location. But it is possible, some few architectures. I think similar thing is also valid for maybe White Rabbit. I'm not going to jump so much, but
no,
it
is. That's why you need something, the concept of boundary clocks, where basically you have like everything is one-to-one, everything is peer-to-peer, and then the splitting is basically on those units, on the boundaries.
Yeah, but that could be a nice. I think White Rabbit has, especially for data communication, right? It's quite good as far as I understand. If they also do an, I would say, analog detection instead of digital, I think they will improve the stability. Okay, this is maybe a hint, but I don't know.
Based here, I think White Rabbit do have boundary clocks. That's exactly why they can scale better, and they do have some level of analog detection, but it's electrical. So on the Ethernet signal, but it's not optical like you are. So it's more limited in terms of the resolution. So.
Yeah, we look forward. Actually, we were trying to do something with an industrial partner. They are a bit of, can I say, rigid, and I don't get much replies. If someone wants to talk with me about a synergy between White Rabbit and these things, I'm open to it. So you have my contact, and we can talk at least.
Yeah. Make sure you add your contact to the slides and
yes,
send
I
it
will
to me
do.
so we can put it on the wiki, like the past as past presentations. Yeah.
Thank you, Ahmed. Yeah, good idea.
Yeah. Anyone else? Okay. Hearing none, we'll thank you again, our presenter, and we'll see everyone. Either we're going to have a call next week, I think it depends, or in 2 weeks. And then we'll go back to the 11 a.m. Pacific. This was like an exception. We basically ran at 10, like on 10 a.m., 1 hour earlier. All right?
Sorry,
Thank you so much.
are these slides available somewhere?
Yes. Just search for timeappliances.com and it takes you to the wiki. And then you have over there links to the video and slides. And then the videos, they're all in a YouTube channel as well.
If you want, I can send a PDF version of it if it's interesting
Yeah,
to you guys.
put the PDF, so I put it basically on the wiki. Yeah, timeappliances.com. Or you can just like go through the OCP thing and then find it. That's just like a hyperlink.
Yes.
All right. Great. Thank you, everyone.
Thank you.
And
Have a
we'll
great
see
day.
everyone in 2 weeks or 1 week. Bye.
Bye-bye.